let's move on. Here is another function that you would like to, here is another example program. Given a number n, I want to find the smallest divisor which is greater than 1. Of course, the smallest divisor of anything is 1, right? We are talking about non-negative divisors. The smallest divisor for any number is 1, but we want something that is different from 1. Okay, so how would one find this? So let's think about it. One could start with 1 and keep going up, right? So here again you need to define two different programs, right? So one function is smallest, let's call it smallest div. Let's say search from 1 to n, okay, and the first argument of this search function will keep on changing, okay. Search at any mn, at any, so what does search do? So in fact you should start searching from 2. What does search do? Search mn smallest divisor of n which is greater than m, which is greater than or equal to n. That's what you want to find, okay. And smallest div of course is the smallest divisor of n which is greater than or equal to 2. So you express smallest div as search to n, and then search mn you can program as follows. Search mn, in case n mod m is 0, mod nm is 0, that means that m divides n, then you just return m, else otherwise you just search for the smallest divisor of n greater than or equal to m plus 1, because you have determined that m is not a divisor, so you have to move ahead in your search, okay. So that's this program. Yeah, so that is the strategy. Try different values 2, 3, etc. to see if any of them divides n. In the worst case you will stop at n because n could be prime, right. Here is the Haskell definition. So I am saying instead of calling it search, I am calling it div search. Search for a divisor n2. I have also switched the arguments. So this particular thing says search for the smallest that's what this is doing. And in general div search mi is to search for the smallest, instead of saying search for, I can say compute. Yeah, compute the smallest divisor of m which is greater than or equal to I. Okay, and this is the same program that we wrote earlier by hand. If m mod I equals 0, then you return I, otherwise you just search from the next integer, okay. This is a nice program, but there are a couple of ways in which you can improve this, right. This div search is a helper function. It does not have much independent use of its own. You will typically have situations where you want to define a function and that requires you to define what are called helper or auxiliary functions, and you do not want to keep defining these at the top level, okay. So usually functions are defined at what is called the top level. if you load a file in GHCI, all functions at the top level are visible. Okay, so if you load a file in GHCI, every function that you have defined at the top level is visible. Visible means that you can write expressions using that function, whereas this div search is perhaps not a function that you would like people to be able to invoke. Okay. So if you load a file in GHCI, you don't want necessarily expressions involving div search. In which case, what you can do is you can make this div search as a local definition, okay, not the top level definition, might not be invoked independently. So you can make it local. There are a couple of ways of making it local. One way is to do var. Okay, this is just like in mathematics or in English or whatever, you will say this is equal to this where f is equal to some g of x, where g is defined as follows. Okay, and that same thing is used in Haskell. Where is the keyword? You say smallest div n is div search n2 where div search, and you just give your definition of this function as usual. Okay, smallest div of n is div search n2 where div search mi is defined as follows. Okay, okay, good. Okay, here there is another improvement possible here, but before that let us look at yeah, so this is the improvement. Local functions can use names defined in the surrounding context. Okay, so if you go back and look at the definition here in div search mi, so you make a recursive call to div search mi plus 1, but the m does not change at all. So it does not feel like there is a necessity to carry this extra argument around all the time in the definition itself. So it is, what is this m? In fact, you will call smallest div n calls div search n2. Let us go back here. Smallest div n calls div search n2, div search n2 will call div search n3, div search n3 will call div search n4, and so on. The n does not change at all. So in fact, there is no need to specifically say div search n2. You can actually do like this. You can say smallest div of n equals div search 2. Okay, and then div search is just from integer to integer. Div search is saying compute smallest what is n? N is defined in the surrounding context. Okay, n is not an argument to div search. Okay, you need not always have this. If something is defined in the surrounding context, you can use it. Okay, so this is the point. So yeah, so this is the improvement. Okay, and the code is also a little cleaner. Okay, of course this n here is not an argument, but it refers to the surrounding context. Okay, but you can see that if you reduce the number of arguments, of course the code will look cleaner. Okay, and you don't physically need to manually need to repeat the same m here as well as here. Okay, when you write the code. Okay. Okay, so here is another way of defining local definitions. So we saw where, there is also let. Okay, you can say smallest div n is let div search I equals this whole definition in an expression. So it will always be let something equal something else in an expression. Okay, you can sometimes put parenthesis here. If you want to define multiple things, then you can say let x equal to something semicolon y equal to something else semicolon z equals something else in some expression involving x, y, z. Okay, this is very useful. there is a subtle difference between let and where. It's not just syntactically you can use let and where interchangeably. Where is part of let. Okay, so here, so when you define something using where, so you say f equals something where you could also say f equals let x equals something in x of x. The difference is that this let is part of an expression. Let can be used as part of expressions. Okay. So, for instance, I can say exp of x1 of okay. I can write programs like this where this whole thing inside this parenthesis is an expression. Whereas I cannot write, this is wrong to write this exp1 why? Because where is part of a definition syntactically, where is part of a definition let is part of the expression. This is a subtle difference. It is okay if you don't get it right now. Okay, just sometimes it will complain if you use. Just know that you can. There is slightly more flexibility with how you can use let. There are some flexibilities associated with where also. As we program more complex functions, we will realize what the difference between let and where is. But for now, you can use let and where interchangeably. Okay, you can. There are two styles of programming of providing local definitions. You can either do something like this thing. You can use where, or you can use let. Okay, these are two styles of local definition. For now, you just need to remember this. We'll encounter some differences later. But if you are doing normal programming, you will not encounter much of a difference between using let and where. You can use either interchangeably. Typically, where is more commonly used, where is more natural in most cases. Okay. 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 So now let's look at that. What is the largest divisor of n? Suppose we want to compute the largest divisor of n other than n itself. We can just say largest divisor of n is nothing but divide n by smallest divisor of n. Okay. And instead of, so here is, we are just introducing some syntax here. Instead of saying divide n smallest div n, where there is parenthesis enclosed, I could have written div n dollar smallest div n. Notice that I have written a complex expression here, some function applied on something else, and I am treating that as one unit, and dollar automatically ensures that. Think of it as dollar supplies parenthesis for you wherever you need them. Okay, and so typically if you have to write f of g of h of x and maybe even more h of I of j of x, then you have to nest lot of parentheses. Okay, and your code sometimes might become unreadable. Instead, you can just write f dollar g dollar h dollar I dollar j dollar. You don't need to write the dollar x. Okay, you can do this. Recall that I mentioned that if I write in Haskell, if I write something like fxy, it should be treated as f applied on x and then the result applied on y. But the moment I put dollar, it treats the thing on the right as one unit. Okay, and here there is another dollar, so it treats this as one unit. There is another dollar here, so it treats this as one unit. There is another dollar there, it treats that as one unit. So Finally, you get back the parenthesis form, but you don't need to write the parenthesis explicitly. Okay. Let's go ahead. Sorry. Yeah, dollar sometimes helps reduce clutter involving nested parentheses. Yeah, so you write things like F dollar, G dollar, H dollar, X plus 1 instead of this. Okay, let's look at a couple more examples. Suppose I want to determine the length of a non-negative integer n. How would you do this? I think we have already seen some ingredients for this. What is the length of a non-negative integer? Let's look at some examples. 323, length is 3. 425, again length is 3. 55,000, length is 5. Okay. 3. So, how do you do this? You compare 323 against 100 and 1000. 323 is between 100 and 1000, and you know that length is 3. Okay. So, really this is what you want to do. You want to start at 1 and you want to keep multiplying by 10, and you want to see when you go above 323, and at that point you will say that that is the length. So, this is one way of doing it. So, you can look for the largest, look for the smallest power really. Smallest power of 10 which is greater than n, which is greater than or equal to n. Okay, this is what you want to do. Greater than n. Right? Fine. So let's look at how we program this in Haskell. If n is negative, first of all, it's an error. So I'll actually I'll call the error function with some appropriate error message. Otherwise, determine the number of digits in n div 2 and add 1. Okay, so this is the thing. Okay, so yeah, so this is the thing. So if n is less than 10, then the length is 1. Otherwise, I want to just say divide n by 10 and then find its length and then add 1 to it. Okay, this is a much more straightforward way of determining the length of an integer. So this is it. It doesn't involve powering 10, etc. Rather, you are dividing by 10. Okay, it's essentially the same idea, but it's easier to specify as an algorithm because you don't talk about power 10, etc. and then compare it with n. Okay, so this is easier. Okay. So let's look at a slightly more complex task, which is that I want to reverse the digits in a non-negative integer. So if I am given the input 1, 2, 3, that should become 3, 2, 1. If I have 1, 4, 5, 6, 7, then that should become 7, 6, 5, 4, 1, etc. If I have 1000, then that should become 1, because technically speaking it is 0, 0, 0, 1, but 0, 0, 0, 1 is, I mean, you ignore leading zeros, and 0, 0, 0, 1 is not a number. Okay, 1 is the number. Okay, okay, good. So this is what we want to do. How would you do this? Okay, here is one idea. So you start with, you do n div 10, that is this. You do n mod 10, that is the last digit. Recursively you reverse this. This whole thing is n. Recursively reverse this and then add this to the left. Add this to the left of reverse of that. Okay. So let's how do you add something? How do you add a digit to the left of a number? So this is some something that is requires a little thought. But remember that we have already defined an int length, right? So if I have 3, for instance, and if I have 423, then the length of this is 3. what I should do is I should multiply 10 by the power 3, which becomes 1000, and I multiply 3 by 1000, that is 3000, and then I add this with 423, that will become 3423. Okay, so to add a digit to the left of a number, I should first determine the length of the number. I should multiply 10 by that length. I should compute the power of 10 where the exponent is equal to that length, and I multiply the digit by that power of 10, and I then add the two. Okay, so this is the idea. So split 13276. So suppose this is an example. Split 13276 as 1327 and 6. You can use div and mod for that. Recursively reverse 1327 to get 7231. Now I need to add 6 at the left. Multiply 6 by a suitable power of 10. In this case, it's 10 power 4. So 60,000 plus 7231 will give me 67231. Okay, so this is the idea in this algorithm. So you use int length to determine which power of 10 to multiply it by. Okay, so yes, so here, so you do as usual. So if n is less than 0, you want to output an error. If n is less than 10, then it's a single digit number. So n itself is the reverse of n. Otherwise, you do int reverse of n div 10. Yeah, this is the recursive call. Then you want to multiply n mod 10, which is the last digit, by an appropriate power of 10. What is the appropriate power of 10? Remember that you want to compute the power 10 of n div 10. Sorry, int length of n div 10. Let's use dollar here. Right, this is what you want to compute. But int length of div n 10 is nothing but int length of n minus 1. It makes writing your program easier. So you raise 10 to the power int length n minus 1. That's the appropriate power of 10. You multiply that with the last digit, and then you add it with the recursively reversed digits of n div 2. Okay. So as we said in the earlier example, what was the earlier example? 13276. You split it as 1327 and 6 separately. You reverse this 7231. You multiply, you determine its length 4. So you multiply, you raise 10 to the power 4 and you multiply 6 by that. You get 60,000 and you add 60,000 to 7231. So 6 times power 10 4 plus 7231 equals 6723. Okay, which is the reverse of 13276. Okay, that's what this program is doing. Okay, so you have a separate function. We are not making this power a local function because power is independently of use. You might want to invoke the power function on some other argument, on some arguments independently of int reverse. So this is the program. So this is a program which is good, which is correct, of course. But you can actually do better. Okay, it's a correct program, but it's a little clunky because you have to do too many things. You have to compute the power of the, you have to compute the length of some number. You have to raise 10 to that appropriate power, and then you have to do such things. Maybe we want to avoid raising to the power totally. Maybe we want to avoid this raising to the power at all, and we also want to avoid computing int length and so on. So how do we do it? Actually, there is a very smart idea. You can actually reverse. Suppose I already provide you a number. Suppose I provide you an accumulator. Say, let us say I have 10, 3, 2, 4. I have some random number I have. And I have this earlier example. What is the example? 13276. I have 13276. Okay. What I can try to do is, I can one by one add each digit at the end of this number to the right of this accumulator. So what I can do is, I can actually first put this here, and then I can put this here. Then I put this 2 here. Then I put this 3 here. What is the result that you have now? You have this number. What is this? This is 10324 followed by reverse of 13276. Okay. So you can see that you pick the digit from the last and add it to the last, but as you keep doing it, things keep getting crossed, right? Because you picked the rightmost digit, you put it at the rightmost here, but once you have removed that, this becomes the rightmost digit, but this is to the left of that, and that you are putting to the right here, so you are automatically reversing, right? The rightmost goes to the leftmost really. Right? As a result of this process, the rightmost digit, which is 6, goes to the leftmost here. It's here. And the leftmost digit goes to the rightmost. That's here. Okay. So this is the idea that we want to use. Why do we want to use this idea? Because adding a digit to the right, adding a digit, call it D, to the right of a number n is very easy. What is it? It is nothing but 10 times n plus d. Right? So this is the idea that we want to use. So we will start with an accumulator and we will keep on doing 10 times n plus d, where d is what you get repeatedly by taking the last digit here. And now what is an appropriate accumulator to start with? 0, right? Because instead of all this, suppose you had started with 0 and then there was 13276 here, then as you see, if I do 10 times 0 plus 6, then I will get 6. If I do, and now let us say I knock this off, okay, and I will get 6 and 1327. And now if I do 10 times 6 plus 7, I will get 67 here, and here I have knocked off the right digit, so that is 132. Now if I do 10 times 67 plus 2, that is 672, and I have 13 here, and then I have 6723, 1 here. Finally from this I have 67231 and 0. Okay, at this point I will stop. Okay, so you can think of it as starting with 0 and some number and repeatedly doing this operation, and you will get, finally you will get some number on the left and 0 on the right, at which point you will stop. Okay, so this is what we want to do. Repeatedly extract the last digit of n and add it to the end of a. This is what we want to do. So this automatically reverses n at the end of a, as we showed using the picture earlier. And if you start with the value of a to be 0, then you are starting with a clean slate and you are doing proper reversal, right? Adding the reverse of n to the end of 0 is just the reverse of n. Okay, and what you do is you use div mod to extract the last digit. So you use div to exclude the last digit and you use mod to extract the last digit, but div mod automatically returns a pair consisting of the number with the last digit removed and the last digit. So for instance, so if I have 25 and I say div 2, I will get 12, 25 mod 2 will give me 1, but 25 div mod 2 will give me a pair 12 comma 1. Yeah, we will see about pairs in a 1 or 2 lectures later, but it's just like using pairs in mathematics. So you just put them within these parentheses with a comma in between. So that's a pair x comma y. So right. So 25 div mod 2 will give you 12 1. Of course, I have to put this within backticks because in Haskell div mod is a function, and to be able to use it as an operator, I have to put it within backticks. So yeah, div mod np is nothing but div np comma mod np, the pair. So here is the function. So int reverse of n, if n is less than 0, I just say error. Otherwise, I reverse n into 0. Okay, so read this as reverse n into 0, right? And reversing some n into an accumulator A is nothing but first compute dm to be n div mod 10. D stands for div and m stands for mod. So this will, so if I have 13276, this operation will return the pair 1327 comma 6, and then what do? If n is 0 originally, then I just return the accumulator, because reversing 0 into any A is just A. Yeah, it's not technically true, but yeah, when n reaches 0, you want to stop. Okay, that's a better way to say it. Yeah, n reaching 0 means stop the computation. Okay, good. So you do this d comma m is n div mod 10. If n is 0, then you just return the accumulator. Else, you reverse d. D is the div, right? Not digit. D is div. Reverse d into A followed by m. Let's just put A followed by m. Okay. So this is the algorithm. So once again, if I start with 13276 and if accumulator is 0, so let's say accumulator is 0, I have 13276. The next recursive call will be to 10 times accumulator plus 6, which is just 6, 1327. The next recursive call will be to 67, 132. The next recursive call will be to 672, 13. Then it will be 67231, 67231, At this point, I want to stop and I will return this as the value. Okay, good. So this is a much smarter way of doing integer reverse. Okay, I'll stop lecture. I'll stop this lecture now. Just to recall, we have seen various examples of writing recursive functions using involving mostly integer and such data types. We have seen how you handle non-termination cases by appropriately invoking the error function, and we have seen that there are smarter ways of doing computing functions and more naive way of computing functions. Sometimes if you just think of a smart idea like this, reversing into an accumulator, then your program becomes much cleaner and the kind of auxiliary tasks that you need to do are much simpler. Okay, clearly this is a much better function than to write than the original one, right? So this int reverse is much more compact rather than the earlier one which involved power, int length and so on and so forth. Okay, so thank you. I will stop the lecture now. We will resume with more material and some demos later. Thank you.